Order. Without objection, the chair is authorized to declare recesses of the committee at any time. And welcome to today's hearing entitled National Laboratories, World-Leading Innovation in Science. And I'll recognize myself for an opening statement. Today we welcome a diverse group of directors from 5 of DOE's national laboratories. They oversee innovative work in basic science and early-stage research performed daily by some of the best scientists and researchers in the world. Our witnesses represent national labs that fulfill the Department of Energy's missions within the Office of Science, Applied Energy, and National Security Programs. The Science Committee's jurisdiction over the DOE budget includes over $9 billion for civilian research, development, demonstration, and commercial application programs, much of which is conducted by the national labs. Over the past 70 years, this research community has led to monumental achievements in medicine, manufacturing, computing, and energy technology development. The labs that are represented here today have made invaluable contributions to U.S. scientific progress and leadership. They have repeatedly demonstrated that basic science research is the most effective way to encourage innovation in technology. In 1942, a group of scientists in Chicago created the first nuclear reactor. 4 years later, Argonne National Laboratory was formed to continue this groundbreaking nuclear research. Using the lab's expertise in materials and nuclear science, Argonne designed the nuclear reactor used in the USS Nautilus, the first nuclear-powered submarine. These reactor designs also became the prototype for most of today's commercial nuclear power plants. The impact of Argonne's research is far beyond what the early nuclear scientists could have imagined. In the 1960s, SLAC National Accelerator Laboratory conducted its first groundbreaking experiments in particle physics using the first linear particle accelerator. This research led to the discovery of quarks, elementary particles that are the fundamental components of matter. Their discovery has changed the way we understand our universe at the most fundamental level. SLAC has led the world in linear accelerator technology for decades, expanding its focus from particle physics to include material science, alternative energy research, biology, and cosmology. Although Sandia is one of the department's 4 nuclear weapons labs, the lab's expertise in science and engineering has broad applications across our economy. In the 1980s, Sandia National Lab collaborated with industry to develop the primary drill bit used in horizontal drilling. Sandia's basic research in geology led to the development of microseismic fracture mapping techniques for hydraulic fracturing. Industry partners adapted these techniques for commercial use and deployed technology to maximize energy production across the country. At Berkeley National Laboratory, a large multi-purpose science lab, researchers have discovered 16 different elements, fabricated the world's smallest synthetic motor, sequenced part of the human genome, and discovered dark energy through the supernova cosmology project. Scientists at Berkeley Lab also developed the genetic engineering technology known as CRISPR, which could one day allow scientists to remove cancerous genes. Finally, Idaho National Laboratory is the nation's premier nuclear technology laboratory. INL scientists have designed and constructed 52 nuclear reactors, including the first reactor to generate electricity in 1951. Today, INL's nuclear expertise supports the military's naval propulsion system, the civilian nuclear power industry, and develops tools to detect hidden nuclear material around the world. DOE user facilities provide our nation's researchers with the most advanced tools of modern science, including particle accelerators, light sources, and supercomputers. Approximately 32,000 researchers each year from academia and the private sector use DOE facilities to perform new scientific research and develop new technologies. Last month, the House passed 3 bipartisan Science Committee infrastructure bills that authorized DOE funds for critical upgrades to a number of high-priority national lab user facilities. In fact, user facilities from 4 of the 5 labs represented here today are included in those pieces of legislation. We look forward to hearing from our witnesses about the potential impact of these upgrades. It is a central goal of this committee to ensure that our national labs remain the best in the world. To maintain our competitive advantage as a world leader in science, we must continue to support the research that will lead to next-generation energy technologies. That concludes my opening statement, and the ranking member, the gentlewoman from Texas, Ms. Johnson, is recognized for her opening statement.
Thank you very much, Mr. Chairman. As a matter of fact, that was an outstanding statement. And I want to thank you for holding this hearing and also from hearing the witnesses from the Department of Energy National Laboratories for testifying today. We look forward to it. Our national laboratories, as we all know, are part of the foundation of the U.S. research enterprise. The work of the scientists and engineers at our labs is truly extraordinary and has been the catalyst for so many scientific and technological breakthroughs. You can look at nearly every growing industry in the United States and see the fingerprints of federally funded R&D, and more than likely see the work of researchers at our national laboratories. Scientific infrastructure and research activities play a vital role in our nation's economic strength as well as its security, and we need to support them. This year's DOE budget proposal submitted by the administration is a slight improvement over last year's, thanks in large part to a budget deal we struck here in Congress. While I'm glad to see the administration is not proposing an overall cut to the Office of Science, I think we can all agree that these vital activities warrant funding increases, not just a continuation of stagnating and declining budgets year in and year out. A key remaining challenge for DOE's Office of Science is that the dysfunctional congressional budget process has prevented new projects and facility upgrades from moving forward. I hope to work with my colleagues in the House and Senate to ensure that we find a way to fund these important projects as soon as possible. Beyond the Office of Science, the rest of DOE did not even achieve stagnation in the budget proposal, and the national laboratories are in line to suffer as a result. The administration is proposing 66% cut to the Office of Energy Efficiency and Renewable Energy, a 32% cut to the Office of Electricity, and a 25% cut to the Fossil Energy R&D, and a 26% cut to the Office of Nuclear Energy. These draconian cuts are simply not acceptable. By all credible accounts, American industry will not fund the activities that are proposed for elimination, no matter how much the administration would like to think so. The department could have heard that from industry directly, but the second year in a row we heard from department officials that they did not formally engage with the private sector in deciding what activities they would cut. However, that did not stop the administration from rationalizing these cuts by stating that the private sector is better suited to carry out activities that are being cut. I hope we can get back to reality during this hearing. I'd like to hear from our witnesses who regularly engage with the private sector about how they foresee the private R&D changing if cuts like those proposed are enacted. In almost every case, research funded by the department is too high risk to attract private sector investment. If the technology matures and the private sector sees an opportunity to profit, I assure you that they will happily find the capital to ensure the technology finds its way to the market. Our challenge has been that we have trouble moving technologies far enough along the innovation pipeline for this to occur. The problem we are facing is not that our federal R&D budgets are too high or that we're doing too much. Quite the opposite. I have not met a single person with actual industry experience who would advocate for smaller federal R&D budgets. Now, to be clear, I am not saying that every program the department currently implements is perfect. We should continue to identify smart reforms and debate our priorities. We must be thoughtful investors of the taxpayers' dollars, but I'm confident that investing robustly in our national laboratories in early and appropriately reviewed later stage R&D is the right decision. With that, Mr. Chairman, I yield back.
Thank you, Ms. Johnson. And I'll introduce our experts today. And our first witness is Dr. Mark Peters, Director of Idaho National Laboratory and President of Battelle Energy Alliance. Before joining Battelle, Dr. Peters served as the Associate Laboratory Director for Energy and Global Security at Argonne National Laboratory. He currently serves as a Senior Advisor to the Department of Energy on nuclear energy technologies, research and development programs, and nuclear waste policy. As a recognized expert in nuclear fuel cycle technologies and nuclear waste management, he is called upon frequently to provide expert testimony and to advise in formulation of policies for nuclear fuel cycle, non-proliferation, and nuclear waste disposal. Dr. Peters received a bachelor's degree in geology from Auburn University and his doctorate in geophysical science from the University of Chicago. He has also completed the Strategic Laboratory Leadership Program at the University of Chicago Booth School of Business. He was honored as a Fellow of the American Nuclear Society in 2015. Our next witness is Dr. Susan Seestrom, Associate Laboratories Director for Advanced Science and Technology and Chief Research Officer at Sandia National Laboratory. Prior to joining Sandia, Dr. Seestrom spent over 30 years at Los Alamos National Laboratory, serving in a number of leadership positions, including Associate Laboratory Director for Experimental Physical Sciences and Associate Laboratory Director for Weapons Physics. Dr. Seestrom was named a Fellow of the American Physical Society in 1994 and served as Chair of the Nuclear Science Advisory Committee for the Department of Energy and the National Science Foundation from 2009 to 2012. In her current role, Dr. Seestrom manages multiple science programs, environmental technologies, computing, modeling, and simulation laboratory-directed research and development, user facilities, and education programs. Dr. Seestrom received her Bachelor of Science and PhD in Physics from the University of Minnesota. She is the co-author of over 140 referred publications with over 1,800 career citations. Excuse me. Our third witness is Dr. Mary Maxon, the Associate Laboratory Director for Biosciences at Lawrence Berkeley National Laboratory. There she oversees the biological systems and engineering, environmental genomics, and systems biology and molecular biophysics and integrated bioimaging divisions, as well as the DOE Joint Genome Institute. Prior to joining Lawrence Berkeley, Dr. Maxon worked in the private sector of the biochronology and pharmaceutical industries and the public sector, serving as the Assistant Director for Biological Research at the White House Office of Science and Technology Policy in the Executive Office of the President. With her extensive background in industry, scientific foundations, and state and federal government, she is a national leader in science and technology policy. Dr. Maxon earned her bachelor's degree in biology and chemistry from the State University of New York, Albany, and her PhD in molecular cell biology from the University of California, Berkeley. Our next witness is Dr. Chi-Chang, Director of the Stanford Linear Accelerator Center, pronounced CSLAC, and National Accelerator Laboratory. Previously, Dr. Cao served as chairperson of the National Synchrotron Light Source at Brookhaven National Laboratory in New York. He joined SLAC as Associate Laboratory Director for the Stanford Synchrotron Radiation Light Source in 2010 and became the 5th Director in November 2012. He has been named a Fellow of both the American Physical Society and the American Association for the Advancement of Science. His research focuses on X-ray physics, superconductivity, magnetic materials, and the properties of materials under high pressure. Dr. Cao earned a bachelor's degree in chemical engineering from National Taiwan University and a doctorate in chemical engineering from Cornell University. Our final witness today is Dr. Paul Kearns, Director of Argonne National Laboratory. With nearly 3 decades of management experience, Dr. Kearns has a strong background in science and engineering, along with extensive experience with the U.S. Department of Energy. Prior to his work at Argonne, Dr. Kearns was the director of the Idaho National Engineering and Environmental Laboratory, where he also served as Deputy Laboratory Director and Associate Laboratory Director for Environmental Technology and Engineering. Dr. Kearns has held leadership and advisory roles in the Department of Energy's Office of Energy Management in Washington and in regional offices, including the Chicago Operations Office. Dr. Kearns is a fellow of the American Association for the Advancement of Science and a member of the American Nuclear Society. He holds a doctorate and a master's degree in bionucleonics and a bachelor's degree in natural resources and environmental sciences, all from Purdue University. Among the 4 experts we have here today, there are at least 50 different titles and an indication of their knowledge and expertise. And so we will begin, and Dr. Peters, if you will lead us off.
Thank you, Mr. Chairman. Chairman Smith, Ranking Member Johnson, and members of the committee, thank you for the opportunity to appear before you today. It's an honor to speak to you about the Department of Energy National Laboratories. I've submitted my written testimony for the record and will summarize it here. My name is Mark Peters, and I'm the director at Idaho National Laboratory. I am also serving in a 1-year term as chairman of the National Laboratory Directors Council, an organization created by the directors of the 17 national laboratories. A rapidly changing world results in a complex and evolving set of challenges for our nation. Primary among those are ensuring our national security at home and abroad, increasing the availability of clean, affordable, and reliable energy, and continuing to enhance U.S. competitiveness in the global market. I am confident in our country's ability to meet these challenges, in part because the U.S. possesses a unique asset, the Department of Energy's national laboratories. Our laboratories are among the nation's top science and technology enterprises with a rich history of accomplishment that has driven American prosperity. This committee's jurisdiction includes the national laboratories, and I believe that each of you can take a great deal of pride in the system you've helped build and support. Our national laboratories are home to state-of-the-art facilities who capably support DOE, the Department of Defense, the Department of Homeland Security, the intelligence community, and our military to provide technical solutions to national security challenges. Finally, our partnership with industry and academia drives technology, science and technology solutions to the marketplace, creating jobs and driving economic growth. But we can never become complacent or be unwilling to honestly assess our strengths and weaknesses and work to improve. I would argue that we can and should strive to do more as a national laboratory system. In October of 2015, the Commission to Review the Effectiveness of the National Laboratories delivered its first report. We all took careful note of the contents of that report, specifically how the relationship between DOE and its management and operating contractors had, in the words of the Commission, eroded over time. My colleagues and I understand our vital mission to serve the American taxpayer is best served by embracing reform and improving the way we operate. I also want to emphasize that the Department of Energy, under the leadership of Secretary Moniz and now Secretary Perry, is deeply committed to the national laboratories and is partnering with us to improve our effectiveness. Last fall, the National Laboratory Directors Council wrote a letter to Secretary Perry in support of DOE's efforts to drive fundamental change across the laboratories. As we continue to evolve the relationship between DOE and its M&O contractors, let us focus on the following areas: rebuilding trust between DOE and its contractors, restoring responsibility, authority, and accountability for decisions and performance, bureaucratic reduction, and when appropriate, the use of consensus standards. We understand that in asking us to be empowered, we also are betting on ourselves, and we need to embrace the culture of safety and transparency. Now, moving on to the focus of the importance of research and development. Idaho National Laboratory is proud of its status as the nation's lead nuclear energy research and development laboratory. As part of our effort to maintain and extend the lives of the U.S. nuclear fleet, we are working with utilities to modernize control rooms and have transitioned DOE's light water reactor sustainability program to one focused on not only helping with extending licenses, but also reducing operating costs. But it's important to note that if we are to maintain our historic advantage in civil nuclear energy, we must establish private-public partnerships between the federal government and the nuclear industry. In that, we are working on advanced reactor designs at the laboratory in partnership with industry. And vital to all that, we must maintain research and development talent, capabilities, and facilities at the national laboratories. This includes a versatile fast neutron source, which I thank the committee for strongly supporting. INL is also a multi-program laboratory that addresses a broad range of energy and security challenges, including protecting the grid from cyber attack. So, in the end, our mutual success requires stability. Maintaining our country's leadership in science and innovation requires sustained and strong support in building cutting-edge scientific and engineering facilities and infrastructure and maintaining an outstanding workforce. Other countries are doubling down their investments in government-funded R&D. This threatens our long-held science and technology leadership position. The National Laboratory System is strongest when DOE is strong. It is absolutely critical that DOE's core missions have strong support and stable funding across the entire R&D spectrum. So in closing, DOE is working actively with the national laboratories to make the system more effective and efficient. Secretary Perry and his team are to be commended for spearheading this effort, which cannot help but result in better outcomes for us all. For our part, we, the laboratories, are committed to working with Secretary Perry and the DOE to build trust and accountability and ensure the best possible return for the nation's investment in the DOE National Laboratories. Thank you again for the opportunity to be here and look forward to your questions.
Thank you, Dr. Peters and Dr. Seestrom.
Chairman Smith, Ranking Member Johnson, and distinguished members of the committee. I thank you for the opportunity to testify today about the role of engineering, science, and technology at Sandia National Laboratories, the nation's largest federally funded research and development center. I'm Susan Seestrom, Associate Laboratories Director for Advanced Science and Technology and Chief Research Officer. There's 4 points I would like to emphasize in my testimony today. The first is that Sandia National Laboratory's core mission is to ensure the safeness, the security, and the effectiveness of our nation's nuclear deterrent. My second point is that our ability to carry out that mission rests on our strong foundation as a science-based engineering laboratory. My third point is that the scientific capabilities that we've developed in executing our mission for the nuclear deterrence are often applied to other missions of DOE and other government agencies. And finally, as an FFRDC National Security Lab, Sandia requires the flexibility to pursue forward-leaning research and development so that we can anticipate and prepare for national security challenges beyond the present scope of programs. As an engineering lab, our purpose at Sandia is to develop advanced technologies to ensure global peace. And that mission sees itself in our nuclear deterrence. As one of 3 NNSA laboratories, Sandia brings foundational science and engineering to the NNSA in order that they can maintain and modernize the nuclear stockpile and ensure its effectiveness in an evolving international landscape. We at Sandia have the responsibility for the weaponization of the nuclear explosives through weapons system engineering and the integration of non-nuclear components into the nuclear explosive packages that are designed by our sister NNSA laboratories. Nuclear deterrence has been our core mission for almost 70 years, and the complex and multidisciplinary nature of that mission has enabled us to solve some of the most pressing national security challenges facing the country in areas such as nonproliferation, energy, and cybersecurity. We conduct such work for a number of government stakeholders beyond the NNSA, including the broader DOE, the Department of Homeland Security, and DoD. This work enables us to strengthen our expertise in key areas, invent new and unique solutions to problems, and to nurture our R&D staff. Our Laboratory-Directed Research and Development Program, or LDRD, is essential to us as our primary source of discretionary research funds. In a future of rapidly evolving threats, LDRD provides us with flexible resources and the agility we need to anticipate and prepare for national security challenges that are beyond the horizon of present programs. Sandia needs its LDRD to invest in long-term, high-risk, and potentially very high-payoff R&D that stretches the lab's science and engineering capabilities. We also use partnering with industry, academia, and other labs to extend our foundational research understanding and contribute results that are important to us and to our partners. I would like to close my testimony with one example of the synergy that I've tried to describe above. There are more examples in my written testimony. A series of projects over 10 years, sponsored by various sources, including laboratory-directed research and development, deepened our understanding of semiconductor physics. Standard semiconductors are susceptible to natural and hostile environment radiation sources that our nuclear weapons can be expected to encounter. We developed a scientific understanding of the rich material science and special processing techniques that allowed us to design radiation-resistant resistance directly into our semiconductor devices at our Microsystems Engineering and Science Applications Capability, MESA. MESA is the only U.S. facility to produce strategically radiation-hardened microelectronics for the nuclear weapons complex. Sandia's rad-hard semiconductor devices reduce the development costs of the W76-1 life extension program, and Sandia is now scheduled to produce more than 40,000 rad-hard integrated circuits for the stockpile modernizations over the next 10 years. With that, I thank you for your attention and the opportunity to testify here today.
Thank you, Dr. Seestrom and Dr. Maxon.
Chairman Smith, Ranking Member Johnson, and distinguished members of the committee, thank you for holding this hearing and for the committee's support for science. My name is Mary Maxon, and I'm the Associate Laboratory Director for Biosciences at Lawrence Berkeley National Lab, a DOE Office of Science lab managed by the University of California. It's my honor to participate in this hearing. Thank you for inviting me. Berkeley Lab was founded in 1931 by Ernest Orlando Lawrence, a UC Berkeley physicist who won the 1939 Nobel Prize for Physics for inventing the cyclotron. Lawrence and his colleagues discovered that scientific research is best done by teams of people with different fields of expertise working together. This teamwork concept is a Berkeley Lab legacy reflected throughout the National Lab complex today. With 5 national scientific user facilities that are used by around 11,000 users annually, Berkeley Lab is a key part of the nation's scientific and innovation infrastructure. Today, we're a multi-purpose lab, delivering world-leading advances in energy, materials and chemical sciences, biosciences, earth sciences, and physics. Other countries are busy building their own national labs. The time is now to invest strategically to ensure that our advantages don't disintegrate and leave us behind. Fortunately, progress is being made from upgrading our light sources to the exascale computing initiative. Positive actions are being taken by this committee and the department to ensure that American researchers have access to the very best, and this is good news. Other areas, more attention is required. Renewing laboratory infrastructure, utilities, water drainage, buildings is needed to support modern research. Although the Office of Science is addressing this aggressively, much more is needed. We encourage the committee to address this long-term challenge. Another long-term challenge is ensuring a diverse and talented workforce at the labs. Cultivating talent and promoting inclusion is central to the creation of a successful work environment, driven by a diversity of thought partners working toward shared objectives. Among the national labs, Berkeley Lab was the first to publish workforce diversity statistics. We know that our success as a national lab depends upon our ability to create a community that brings together people with diverse backgrounds, points of view, and approaches to problem solving. This is critical. In my remaining time, I'd like to describe how the labs succeed by integrating unique resources and world-leading expertise. National labs play a key role in our innovation ecosystem, uniquely talented, equipped to tackle grand challenges by integrating resources and expertise at a scale and breadth impossible by other institutions. The labs also provide a longer-term outlook on success than is available within industry, one that can take science from the bench to the user facility and ultimately to collaboration with industry and the marketplace. One really exciting example is the microbiome for energy and environmental sustainability. It's got great promise, but it's a tough scientific nut to crack. Microbes are the most abundant life form on Earth. In a handful of soil, there are more microbes than stars in our galaxy. They exist in a network of communication and collectively work to impact their environments, whether healthy soils for agriculture or the biodegradation of toxic pollutants. Deciphering this world of microbiomes is a huge undertaking. It's like taking 1,000 puzzles, each with thousands of pieces, and then scattering them in a pile and trying to reconstruct them without a picture. It requires a national lab. Genome sequencing, engineering biology, advanced high-performance supercomputing. Success here could mean more productive energy crops, faster remediation of contaminated soils, and new bioproducts to fuel the nation's bioeconomy. In this and other examples, there are no bright lines between fundamental research, applied R&D, and commercialization. It's a continuum. The national laboratories work well along this continuum and play a key role in shepherding discoveries to the point of commercial viability. A recent example is the Agile Biofoundry. Established in 2016 by EERE, The BioFoundry is a biological engineering platform that aims to reduce the time and cost of producing biofuels and bioproducts, a difficult challenge. The BioFoundry is a consortium of 8 national labs established in response to industry, the need that was articulated at listening days with industry representatives. They specifically identified issues that are beyond their capacity to address. It's now a scientific platform de-risking a number of technologies, and a recent solicitation shows that there's a significant demand for this type of research. 19 companies applied for $20 million in requested funds, 4 times more than was available. I thank you for the opportunity to testify at this important hearing. I'm happy to answer your questions.
Thank you, Dr. Maxon and Dr. Cowell. I still don't think your mic is on.
Oh, I need to push.
There, okay.
Chairman Smith, Ranking Member Johnson, and members of the committee. My name is Chi-Chang, the Director of SLAC National Accelerator Laboratory. I'm happy to be here to talk about how SLAC is leading the way of basic research and innovation in the United States. SLAC, located on Stanford campus in Menlo Park, California. Laboratory is one of the 10 Office of Science labs. We have an annual research budget around $300 million, with another $280 million in fiscal 17 to construct 2 new large user facilities. SLAC was established in 1962 as a center of particle physics, as the chairman described at the beginning. The laboratory has evolved over the last 10 years into a multi-program labs. The focus of the laboratory is on fundamental science, discovery of the things that we don't know about nature. The work has led to 4 Nobel Prize winners over the last few decades. Let me give you 2 examples. In the laboratory today, operate 2 major X-ray facilities. One of them is Stanford Synchrotron Radiation Light Source. The other one is linear coherent light source. Linear coherent light source is the world's first X-ray free electron laser. Free electron laser is a very different kind of X-ray source. It comes in very short time, 1 millionth of a 1 billionth of a second, the time scale in which electrons move, atoms moves. It allows us to take snapshots to make movies out of how things actually works in nature. And after the machine was built in 2009, there was an international competition, both from Europe and Asia, tried to duplicate what we have done. And so there is a LSOS-2 project currently ongoing, and then a LSOS-2 high-energy upgrade beyond that. These 2 projects are made possible because a multi-laboratory collaborations between the Fermi Lab, Argonne National Lab, Berkeley Lab, and SLAC that allowed us to make it happen quickly and have the technology better than our competitors. And when these 2 upgrades been completed in mid-2020 timeframe, we will have the world's most powerful X-ray facility available to scientists around the United States to research on materials, chemistry, biology, and applied energy programs. These will lead to better electronics, batteries, new drugs, and also new materials like quantum materials that may be important for quantum computing in the future. SLAC is also participating in a collaboration between the National Science Foundation and Department of Energy, High Energy Physics Office, where we are building the Large Synoptic Survey Telescope. This is the largest digital camera made to survey the sky, half of the southern sky in every few days. That data will be made available to everyone in the country, even the high school students. They can look at this to understand the mysteries we still don't know about dark matters and dark energies. And in partnership with DOE, SLAC and Stanford University have developed a new M&O contract. That new contract allowed us to streamline processes that we use, give back autonomy and local control to the laboratory so we can be more efficient and more effective in utilization of the resources that we have. Finally, in the last 55 years, SLAC has made a significant contribution to basic science. With those contributions serve as a basis for future, the 1,500 staff at SLAC are looking forward to a future so we can make even more contribution after these facilities are built. I'm happy to be here today, and thank you for the invitation. Looking forward to the questions.
And thank you, Dr. Cowell and Dr. Kearns.
Chairman Smith and Ranking Member Johnson and members of the committee, thank you for the opportunity to appear before you. It's my honor to join my colleagues from Idaho, Lawrence Berkeley, Sandia, and SLAC to speak about the national laboratories and the world-leading innovation they deliver. I am Paul Kearns, Director of Argonne National Laboratory. Argonne is managed by UChicago Argonne LLC for the DOE Office of Science. At Argonne, our research pushes the boundaries of fundamental and applied science to solve complex challenges and develop useful technologies that transform the marketplace and change the world. In fiscal year 2017, Argonne employed 3,200 people in the Chicago area. Our budget was $751 million, with approximately 80% of the funds from DOE and the balance from the Department of Homeland Security, other government agencies, and the private sector. Argonne's major strategic initiatives are targeted to deliver breakthroughs in science and technology in areas that support DOE's mission and reflect our vision for the future. They include hard X-ray sciences, advanced computing, materials and chemistry, manufacturing science, and the fundamental study of the universe. Our unique scientific facilities include a world-leading X-ray source, particle accelerator, supercomputers, and a nanoscale science center. As a nexus for thousands of visiting researchers and collaborators, these facilities extend Argonne's impact beyond our own laboratory. At the Advanced Photon Source National User Facility, we use hard X-rays to characterize materials at the atomic and molecular level to understand, predict, and control their properties. The APS is helping Argonne make additive manufacturing more reliable and hypersonic flight possible. One of the most successful drugs used to stop the progression of the HIV virus into AIDS got its start at the Advanced Photon Source. The Advanced Photon Source upgrade will create a world-leading ultimate 3D hard X-ray microscope, enabling researchers to observe individual atoms interacting in real time. This new microscope will make it possible to see changes at the molecular level, such as before a steel girder starts to crack, before a healthy brain succumbs to Alzheimer's, and before electric car's battery begins to fail. At the Argonne Leadership Computing Facility, 2 of our supercomputers are among the 20th fastest in the world. We've applied our high-performance computing to challenges in energy, materials, extreme weather, and more. The ALCF is part of the multi-lab initiative with the National Cancer Institute and the Department of Veterans Affairs to apply big data and artificial intelligence to healthcare and genomic data to determine optimal treatments, improve outcomes, and reduce cost. In 2021, ALCF will welcome Aurora, an exascale system that will be at least 50 times faster than the most powerful supercomputers in use today. Argonne's efforts in exascale are part of DOE's larger exascale computing initiative. Argonne's knowledge and facilities coupled with our approach to deploying these assets distinguishes us as an institution. We work across the continuum from basic discovery to use-inspired to translational science in order to deliver positive societal impact. Conventional wisdom states that translating scientific advances into impact is a decades-long process. The national laboratories, as you heard today, have long worked to accelerate this process by enabling researchers to execute more experiments in the same amount of time. Advanced computing in the form of deep learning, machine learning, and artificial intelligence is providing a powerful new boost to the speed of discovery. Argonne's energy storage work dating to the 1960s is an excellent discovery to impact model upon which to build. In the mid-1990s, the DOE supported investigations aimed at a more stable and greater capacity electric vehicle battery. In 2000, we patented our signature battery cell technology, and in 2007 began licensing it for mass production. In 2011, our technology made its market debut in the Chevy Volt. When it comes to next-generation batteries, the Joint Center for Energy Storage Research, JCESR as we love to call it, which is led by Argonne, partnering with 20 other entities, has literally and figuratively changed the formula. JCESR has yielded revolutionary new battery materials in an operations model to optimize entities from many sectors working together. We're taking our energy storage experience to new frontiers, including catalysis and materials for clean water. We're also working on quantum materials, which promises nothing short of a revolution in computing speed and accuracy. Argonne and the University of Chicago have set up the Quantum Factory, an experimental facility, and have collaborated with Fermi National Accelerator Laboratory on the Chicago Quantum Exchange to enable graduate students to learn from national laboratory scientists and academics. America's national laboratories are powerhouses of science and technology. My fellow laboratory directors and I appreciate this committee's continued support for the national laboratory system and your commitment to leadership in science and technology. Our national laboratory infrastructure is the envy of the world. The DOE and its laboratories are advancing projects that will keep the United States at the forefront of innovation for decades to come. Lastly, before I close, I'd like to thank this committee for its leadership in advancing legislation through the House of Representatives to improve and update critical science infrastructure across the national laboratory complex, including H.R. 4377, the Accelerating Americans' Leadership in the Science Act, which, among other important priorities, authorizes funding for the APS upgrade project. Thank you for your time, and I welcome your questions.
Thank you, Dr. Kearns. Recognize myself for questions, and let me address my first one to Dr. Peters. Dr. Peters, in your prepared testimony, you expressed some concern that the national labs are losing their position as trusted advisors to the Department of Energy. What steps is DOE taking to maximize the effectiveness of labs, in your opinion?
Thank you, Mr. Chairman. The department's re-engaged us as a group in a really meaningful way. As I said in my summary, it started with Secretary Moniz, and it's continued with Secretary Perry and his team. So we have active, nearly day-to-day engagement with them on aspects related to how we operate the laboratories, but also, more importantly, the strategic directions of the department. And particularly now with the undersecretaries in place, there's a lot of back and forth about research priorities and whatnot. So I think we would collectively say the partnership's headed in the very positive direction.
Okay, good. Thank you. And Dr. Kearns, we talked about this earlier today, but you mentioned that J. Caesar's goal is to develop next-generation batteries that deliver 5 times the energy at 1/5 the cost. I think we all know that the key to success for encouraging the use of alternative fuels and energy is a better battery, a more efficient battery, a lighter battery, and a battery with greater storage. And when we have that breakthrough, we'll, I think, change the energy world. How close are we to developing that kind of battery, the kind of battery that you've been working on, the 5 times energy at 1/5 the cost?
Progress has been substantial. Significant progress is being made. I'm happy to report that by working with our colleagues from 4 of the other national laboratories and 5 universities, along with the members, the representatives, if you will, from industry, we've made good progress in terms of discovery of new materials that are less expensive. They do allow greater energy storage, energy density to be stored, and will last much longer. So significant progress is being made. We've achieved the cost objectives that we talked about in terms of 5 times less expensive in terms of the materials that have been discovered through J. Caesar. We've made good progress as well in terms of energy density. The developments apply to both grid and transportation, if you will, storage technologies. I'd also report that we've had 3 spin-out companies, technologies that people have come and taken a look or perhaps helped us develop and then taken to really into the innovation pipeline to really result in commercial scale products. So progress has been good.
Okay. Would you want to hazard a guess when such a battery would be commercially available?
I'm afraid, well, I don't think I can really guess that.
How about an order of magnitude?
Okay. Okay.
Next
well,
2 to 3 years,
yes.
maybe?
The pace of innovation is accelerating. You know, I think certainly within the next 5 years, we'll see a very dramatic change in the field of energy storage, both in terms of grid and transportation technology.
Okay, good. Thank you. Final question to all of you all, and that is, what steps are the national labs taking to reduce the cost of nuclear power? We all know that nuclear is clean, it's a little expensive. If we're going to encourage the use of it, we need to reduce the cost. So what steps are you taking, and how optimistic are you that we will be able to reduce those costs? And I guess we'll just work our way through Dr. Peters and then Dr. Seestrom.
Thank you, Mr. Chairman. First, on the existing fleet, as I summarize the DOE's light water reactor sustainability program that INL and Oak Ridge and Argonne all have a role in is focused on trying to not only sustain the existing fleet, but also drive down operating costs for the existing fleet. So that's one. In advanced reactors, I think going to modular construction, modular manufacturing and construction, but the advanced reactors, I think, are the opportunity to really do research and development to try to drive down system costs, because the economics of nuclear it's probably the thing that has to be addressed.
Great. Dr. Seestrom?
No comment on this one.
Okay. Dr. Maxon? No comment?
No comment here.
Okay. Dr. Kao?
No comment.
Oh, my gosh. You don't have, I mean, there's an old adage that scientists should be able to talk 1 minute on any subject. But we won't push you. And Dr. Kearns?
I will offer a couple of thoughts, and one is, as Mark mentioned, Dr. Peters mentioned, we're very active in terms of collaboration with both Idaho and Oak Ridge and Advanced Nuclear Energy. And one of the current efforts underway that I think is really a great model in terms of working with industry is GAIN, the Gateway for Acceleration of Innovation in Nuclear Technologies. And so we're really pleased to be a part of that. And Mark probably can speak more eloquently than I to the impact, but it's really a wonderful opportunity, if you will, for companies interested in nuclear technology, developing advanced reactor technologies, to really come and engage with the department and its laboratories, use our facilities and partner shoulder to shoulder with our researchers. And so it's really a great opportunity in that way. Let me pass it back to Mark in case he wants to say anything more specifically on GAIN.
Okay.
Is that okay, Mr. Chairman? Could I just elaborate a little bit? Yeah, thanks, Paul, very much. And I would tie it back to this committee's had a lot of discussions about R&D test beds and the ability of government sites to ultimately demonstrate technologies. That's what GAIN is. That's what the Gateway for Accelerated Innovation in Nuclear is. So what y'all are talking about in your deliberations is actually starting to happen out there.
Good. Okay, very good news. Thank you all, and the ranking member, Ms. Johnson, is recognized for her question.
Thank you very much. To all witnesses, if the President's proposed budget for fiscal year 19 was enacted, DOE's renewable energy R&D portfolio would see a 60% reduction. The sustainable transportation budget would get a 70% cut, and energy efficiency activities would be cut by 80%. It would cut critical research on the electric grid by over 50% and would cut nuclear energy and fossil R&D by 25% each. And it would eliminate ARPA-E and the Loan Programs Office. I'd like each of you to please describe the impact of these proposed cuts on the research capabilities and personnel of each of these labs. And then what are the consequences of drastically reducing U.S. R&D for U.S. competitiveness in a globalized economy?
Thank you, Member Johnson, for the question. So I'll speak at it from the perspective of the applied energy programs, because that's really what would affect INL. So we get funding from the Office of Nuclear Energy, Energy Efficiency and Renewable Energy, and the Office of Electricity, all three. If those cuts as proposed were to be realized, we as a laboratory would have effects and capabilities in applied material science and engineering, in chemical engineering and nuclear chemistry and nuclear engineering, as well as in user facilities. So we wouldn't lose capability, but we would have impacts on those capabilities. Now, I don't have to remind you that this is a process, and so, but the numbers, if we took it at face value, would be order 10% of the INL workforce. But watching the process play out, I'm not anticipating significant reductions once Congress weighs in, and we'll respond to Congress's appropriations.
Mm-hmm. Thank you, Congresswoman. Sandia has a substantial portfolio in applied energy programs, roughly $140 million. Without seeing the details of the cuts, it's hard to say the exact impacts to our programs, though it's surely true that many deliverables would be slowed down. Because of our broader national security portfolio, we have some ability to move staff between our energy programs and other programs in the lab, so we don't anticipate that we'd have any reductions in force, but certainly lose traction on important research.
At Berkeley Lab, I guess I would say the same situation is true, that without the details, it's really hard to know how these cuts would manifest. That said, we could predict something on the order of 100 FTEs lost in particular areas at the lab. I mentioned the Agile Biofoundry as one particular collaboration facility that's funded by EERE. There would be serious impacts to that, and that affects not only academic users, but also industry as well. And finally, I would mention a Flex Lab, which is a fully instrumented collaboration facility that's used by a large number of academic and industry users. There would be some serious effects there as well.
For SLAC, Congresswoman, since we have a relatively small program in ERE, so the impact is relatively small.
And at Argonne, about 10% of our funding comes from the applied energy programs. And much like my other colleagues here, it's a little hard to know really what the impacts would be without the specifics of the program in terms of where the cuts would be made. I will say Argonne works across the spectrum, as I talked about, that continuum from discovery science to use-inspired to translational science, and certainly funding for the applied energy programs really allows us to complete that continuum, if you will, and really work closely with industry. So we're strong supporters of the applied energy portfolio in the department, and would encourage the committee and Congress in general to continue its hard work on behalf of those programs.
Could you comment on the elimination of ARPA-E? Either one.
I mean, INL doesn't currently have active ARPA-E projects, so I can't speak at it from the lab's perspective. I will say that from the broader perspective, in my opinion, I've watched ARPA-E and I've seen a lot of success come out of ARPA-E.
Yeah, I would also add, if that's okay, to that comment by indicating that ARPA-E, one of the requirements for funding there is that we bring an industry partner, or the industry partner brings a laboratory, if you will, to apply for the funding there. And so it's a great model of working with industry, I believe.
Thank you very much. Time expired.
Thank you, Ms. Johnson. The gentleman from Oklahoma, Mr. Lucas, is recognized for his questions.
Thank you, Mr. Chairman, and I thought that 1-minute rule on any subject applied to members doing town meetings. Weak attempt at humor. Dr. Maxon, in your prepared testimony, you discussed Berkeley Lab's extensive work in fundamental biological sciences, as well as technology to create better biofuels, more resilient crops, and bio-based chemicals. And in all fairness, I have the privilege, in addition to serving on this great committee, of serving on the Ag Committee, and I'm a farmer by trade. So let's expand for a little bit. Could you provide more information on how researchers at Berkeley are improving these processes?
Thank you for that question. I'll take a shot at that. From an agricultural perspective, I mentioned the microbiome science, that the uncharted territories of the billions of organisms that are in every gram of soil. One could imagine that with a deeper understanding of how these microbial communities communicate with each other and influence the environments around them, it's not too far-fetched to suppose that there would be opportunities to improve through the soil itself, abilities to provide fewer inputs to the soil, that crops would be able to get along with less water, less fertilizer, because the microorganisms themselves could be enhanced to deliver those nutrients like nitrogen and phosphorus directly to the crops.
Along that line, your testimony mentions the Joint Bioenergy Institute, JBAE, and looks at improving those bioproducts at the molecular level. Give us some examples of how JBAE can accomplish this, but only in a national lab kind of an environment.
Yeah, thank you. So you can imagine that one such bioproduct could be an enhanced biofuel crop, one that's got more sugars to convert to fuels or chemicals that are desirable, and as well as the chemicals themselves. One can imagine that new types of plastics with higher desirable properties and thermal behaviors, as well as, for example, enzymes. Laundry detergent enzymes are ones that we use every day. That particular market, for example, is on the order of $6.2 billion. So being able to do end-to-end scientific discovery from discovery to use inspired, and then hand off to companies is something that the national labs, in J-Bay particular, is very good at.
Taking this one step further, I'm also fascinated by the nexus between high-performance computing research at Berkeley and the progress in the biological sciences, particularly how Berkeley is using the supercomputers to analyze massive amounts, and I think that's the appropriate phrase, massive amounts of biological data to learn more about everything from microbes to biofuel. What are the limitations to today's computing systems when you're trying to solve these complex biological challenges?
We, as biologists, are, I would say, a bit behind some of the other fields, such as physics, in big data understanding and approaches. So I think one of the limitations is trying to port, if you will, our bioinformatics approaches that we use today to analyze genomes and predict protein clusters and those important aspects to a high-performance setting. We don't have the right kinds of algorithms, and biologists and computing scientists don't even speak the same language. So I think one is technologies themselves. I think the other is bringing the disciplines together to work more productively, like physicists and computer scientists do.
Expand for just a moment on the technology side of that equation, the physical part, where you need to be going.
Yes, so this is not my area of expertise, but when you think about using computers that have multiple cores, that means the algorithms run very differently than the computers that don't use multiple cores. And so the things that we are set up to do today, let's say analyzing a genome, can take on the order of, 40 days. Transporting that with new hardware and new software to a high-performance platform, you can do the same type of analysis about an hour.
Thank you, Doctor, and I would hope my dear old freshman agronomy professor from Oklahoma State, Mr. Chairman, be proud that I focused on the important issues. Thank you. Yield back.
Thank you, Mr. Lucas. The gentlewoman from Oregon, Ms. Bonamici, is recognized for questions.
Thank you very much, Chairman Smith and Ranking Member Johnson and all the witnesses, and happy Pi Day. Before my questions, I want to recognize Mohammed and Rayleigh, who are high school students from Oregon, who are here today. They are finalists in the Regeneron Science Talent Search. So please welcome them and keep your eye on them. They are our future leaders. So to the witnesses, President Trump has released his budget for 2019, and I'm very concerned with many of the proposals. Our nation is dealing with a growing global demand for energy, we have an over-reliance on fossil fuels and harmful emissions that are contributing to climate change. We need to be investing more, not less, in research and development programs, especially to keep our air and water clean. Oregon has been a leader in renewable energy projects, and I'm interested in hearing from our witnesses about how to advance these efforts nationwide. Dr. Kearns, I'm glad you're here today with your background at the Pacific Northwest National Laboratory. The office in Portland has led efforts to improve energy efficiency in residential and commercial buildings, to strengthen renewables such as wind, water, solar, and to expand storage systems for electric vehicles. The innovative work of labs like PNNL benefits from consistent federal investment, but unfortunately, Congress has been governing crisis to crisis with a series of short-term continuing resolutions. That lack of consistency affects research, but it also affects infrastructure. For example, facility upgrades or new construction cannot begin. The U.S. is competing, as we know, against other countries that have dedicated significant long-term funding to science and research. So could each of you discuss your perspective on how the lack of stability in funding has affected projects at your labs and how that affects our global competitiveness? And I do want to reserve a little bit of time for another question. Dr. Kearns, would you like to start?
Certainly, as Dr. Peterson commented in his introductory remarks, stability and funding is really critically essential for, if you will, working across that continuum of research that I spoke to in terms of discovery science, use-inspired science, and translational science. And so it's important that there be a stability funding so that one can do the needed planning and actually conduct the research and have it proceed in a way that allows accomplishments or expectations to be realized. So it's very critical in that regard.
Thank you. Anybody else want to add on to how the lack of consistency in funding has affected your work?
Maybe I can add something. So a lot of us actually are involved in construction of major projects. These funding profile, if you have a continuous resolution, if you're on the upswing curve, you're stuck with a lower level from the year before, that tend to extend the total length of the project and increase the cost.
Does anybody want to comment on how that lack of consistency is affecting our competitiveness globally? Dr. Seestrom, I know you look like you're ready to speak.
So I would make two comments. One, that I think it's quite scary globally. You know, several of our staff recently returned from Solar Energy Conference in China, and their work is quite impressive. They have large efforts in renewable energy. I think that other countries aren't slowing down, and you know, our scientists can work on many things, and when we have funding shortages, they will walk with their feet to the things that are funded. I'll mention from our NNSA mission, not energy specifically, but you know, funding delays have impacted one of our major starting LEPs, the WAD-4. It's hard to do any new project when you have continuing resolution.
Right, and I'm going to ask Dr. Kearns, Dr. Maxon, what role does energy storage play in promoting clean energy? For example, at the National Energy Technology Laboratory in Albany, Oregon, where they're currently developing sensors and controls that enhance the efficiency of power plants and the electric grid. Their efforts should be a model. Energy storage has implications, of course, for national security and competitiveness as we move toward lower emission and zero emission energy sources. So what about energy storage and promoting clean energy, reducing emissions, and increasing efficiency of the grid? Is our nation staying competitive in energy storage technologies? Dr. Maxon?
Energy storage technology is not my area of expertise, but I do know that at Berkeley Lab there is an industry consortium that spun out of our focus on energy storage. And this industry consortium called CalCharge is enabling the stakeholders to work together and collaborate in whole new ways to accelerate more technology development. I would say, though, that it's very likely that with a more consistent funding profile that we would see more advances more quickly.
Thank you, and I see my time is about to expire. Thank you, I yield back. Thank you, Mr. Chairman.
Thank you, Ms. Bodemichi. The gentleman from California, Mr. Rohrbacher, is recognized.
Thank you very much, Mr. Chairman, and thank you for your leadership over the years and this and other issues where you have provided us great hearings like this that are expanding our understanding of science and the important role that people like this are playing. So thank you very much. Mr. Chairman, one of the things that I have been frustrated about with the scientific community, and maybe it shouldn't be frustration in the scientific community, I'm going to ask you your opinion on that, is we seem to be still basing our electricity production on things that are either risky or too dirty, you know, and or something like that. Maybe could you, and I have understood over the years that we actually have the capability of producing, for example, a next generation of nuclear power. In fact, Dr. Peters, you mentioned that research. Where are we right now in getting away from light water reactors and into the next generation of reactors that are safer and actually have a lot of potential? Where are we at that?
So thank you, Congressman. So first on the existing fleet, I wouldn't characterize them as dirty or unsafe. That would be my first comment. They're operating safely and securely, and they will continue to do so for decades. That said, there is an exciting number of new advanced reactor concepts that are emerging.
Well, I was actually talking about other sources.
I figured. I thought I'd put that in there.
Okay.
I won't go with the other part of this. But the advanced reactor, there's a lot of companies that are emerging. I know you're familiar with General Atomics. They're not emerging. They've been around for a long time, but they've got some interesting concepts. There's startups that are popping up, and they're working with the labs. So some of those companies are talking about having first commercial in 2025 to 2030.
We actually have prototypes working of the next generation of nuclear power.
When can we?
No. Do we have it?
We do not.
Now? And we've spent billions of dollars of research on this, and yet we don't have even a prototype working. Now, is this lack of progress due to being stymied by scientific obstacles that we can't seem to get past, or is this a result of regulation and bureaucracy?
It's actually I'm not a company that's trying to innovate and develop a concept, but I would tell you, they would probably tell you it's capital. finding private capital to take it to the next step is probably their biggest hurdle.
Capital, but we have, in the meantime, we've spent billions of dollars supposedly on research.
And we've done that research, and so they're prepared to take it to commercial, but they have to seek significant private capital to take it to the next step. There's a partnership with the federal government, but you can't expect the federal government to carry the entire freight for commercializing their units, so they're going to have to find additional private capital.
Well, I would hope that that would be one of our major goals, is to finally have, with all the great research that has been done on getting us away from light water reactors, which I believe are dangerous, and leave us with basically pollution, or in the sense that we have to store the nuclear rods forever. We should get away from that, and we should be going on to this next generation. And so, thank you very much. I would hope that that message gets through. One, and on the end there, Mr. Kearns, you were talking about the batteries. In the chairman's hometown in Austin, Texas, Dr. Goodenough has supposedly had a breakthrough, and a major breakthrough on this. Would you say that this is accurate? Is it a breakthrough, or is it being hyped?
I'm not, unfortunately, I'm not that familiar with the breakthrough that's been described. I've read some things in the press. It sounds impressive, certainly, and certainly would pay a great deal of respect to Dr. Goodenough. I think it certainly warrants some additional follow-up.
And Mr. Cow, you were shaking your head yes about, you know about that project?
Yes, but like all science effort, you need more people to go into it, to repeat, and to make sure it's all correct.
But would you say that on your preliminary look on this?
Concept, yes.
So okay. We had another panel here, of course, talking about that, about batteries, and most everybody gave it a good thumbs up. What we are interested in making sure is that the money that we are spending on research actually is not done for the sake of research, but instead is done to make sure we're doing things that improve the life of the people on this planet. And that's why I'm sort of trying to focus on the next generation of nuclear power and things such as that. And we're behind you, and we want things to be done more efficiently, but we also want to make sure the results are actually put into practice in a way that will improve life. So thank you very much. Thank you, Mr. Chairman.
Thank you, Mr. Rohrabacher. The gentleman from California, Mr. McNerney, is recognized for his questions.
Well, I thank the chairman, and I think I cut in front of the gentleman from New York. But he's not yelling. Okay. But he's going to let me do this. I'd ask, could anyone on the panel enlighten me on the distinction between early stage and late stage research, or is that sort of a fantasy to think that there's such a distinction? Anyone on the panel want to take that?
So there are different ways one talks about research. The DoD uses technical readiness levels. It's a continuum, as I think Dr. Maxon said. You know, we like to think about it in terms of basic research as a national security lab. We do a bit of that, but our focus is on use-inspired, going to really applied research. I think the key distinction is how you can cross that valley of death between when you know the science and the technology, but the receiving end in industry is not yet sure enough to invest their money to see they have a product.
So I've heard a lot about the Valley of Death. In fact, I was in industry for a while, so I know personally about it. Wouldn't it be better to think of it on a case-by-case basis than saying, well, there's early stage and late stage research, and we have to defund late stage research?
So I do not see that it's useful to talk about defunding any research based on that distinction.
Thank you.
Sir,
Sure.
may I real quick? To your last point, I would draw out nuclear energy as it is case by case in some sense. The federal government role for getting to commercial nuclear energy technologies is different perhaps than it might be for another energy technology. And as you know, there's been a long-standing federal partnership with the private sector. But you know, doing the science, doing the applied science, but actually going out to first-of-a-kind demonstrations for some of these advanced technologies there's probably an important government role in there. So that's important to remember.
Well, thank you. And there's some significant cuts we're seeing in the administration's budget. you got to think that the valley of death is going to get wider with that sort of a cut. Is that a good assessment? I see head shaking, but that's about it. Nobody wants to speak up. Given the budget cuts, does anyone want to talk about a specific program that they like that's going to suffer from this? I mean, fusion, for example, we're going to suffer because we need to be invested in ITER, even though it's taking place overseas. America gets a lot of bang for that buck. Are there any other programs that anyone wants to talk about that are going to see harmful cuts that are going to harm our national interests? Yes, Ms. Maxon.
I'd like to mention that for the Department of Energy's Biological Environmental Research Program, there are some serious proposed cuts to earth and environmental sciences studies. And from my perspective, if you think about understanding the subsurface, this is important because that's where carbon, nitrogen, phosphorus, all these building blocks of life are. And that particular program that I just mentioned studies the watershed system and how the water, what about drought resilience and how do the nutrients and contaminants move underground? I think that's a very serious, that would be a very serious loss, our ability to predict resilience in local communities to extreme weather.
Well, since I'm from California, I sarcastically don't care about drought resilience. Yes, Dr. Kearns.
Yeah, I just would like to build on that a little bit in terms of biological and environmental research. One of the key things that's underway there in the Earth and Environmental System Sciences program is really the evolution, if you will, or further development of, if you will, our Earth systems computer models to actually run on our new exascale systems. And so it's a critical component that requires continued investment, continued support in terms of funding. And it does really, development of enhanced models here really improves our ability to understand the global hydrologic cycle. It gives us deeper insights, as been mentioned, into future droughts, floods, wildfires, and other concern I know in California, and hurricanes and agricultural sustainability as well. So many topics that have been touched on here today, so critically important that we continue to invest so that we can further our understanding.
Are the labs an important element in bringing together scientific collaboration? Is that going to be harmed by these kind of cuts? Yes, Ms. Maxon, Dr. Maxon.
It's my opinion that the labs are really an integrator of communities of researchers. You've heard about the scientific user facilities. That's an obvious example. But there are other programs, like, as mentioned before, the Joint Bioenergy Institute, for example, that brings together universities and national labs and companies to work together on problems. So I do think that this is seriously at risk, the integrator function and collaborations.
Thank you. Mr. Chairman, I'll yield back.
Thank you, Mr. McNerney. And the gentleman from Texas, Mr. Weber, the chairman of the Energy Subcommittee, is recognized.
Thank you, Mr. Chairman. Dr. Peters, I'm going to move over here a little to my left. It'll be one of the rare times I do. This committee has taken a leading role in advocating for advanced nuclear energy research. Specifically, my bipartisan nuclear energy research legislation has passed the House on multiple occasions. This bill would authorize the construction of a research reactor, versatile neutron source. I wish the gentleman from California was here, Ms. Rohrabacher, heard this questioning, which you mentioned in your testimony, the nuclear versatile neutron source. And it'll open up for national labs for the development of prototypes for advanced reactors. That's the aim. So, Dr. Peters, why is it important, in your opinion, for the Department of Energy to invest in a research reactor?
So thank you, Mr. Chairman. Thank you for all the support of what we do. So just quickly, we do operate test reactors already. INL operates the advanced test reactor and the transient test reactor, 2 large reactors. The high flux isotope reactors operate at Oak Ridge. So they operate at a certain, not to get too much into the physics, but they produce thermal neutrons as opposed to fast neutrons, which your new proposed reactor would do. So we have that capability, but if a company or a university professor or a lab person wants to do research on materials that would be apropos to a reactor that's operating in a fast neutron spectrum, they have to go to a place like Russia or a place like China to get those fast neutrons. So right now, the United States does not have that capability.
Right, and that's unacceptable. I think Dr. Maxon said earlier about companies are reluctant to invest until they see the dependability of something coming on. So if the United States does fall behind, you mentioned Russia and China, that has international implications in nuclear research.
It does, and it also has national security implications more broadly. If we don't have a strong civil nuclear sector, we don't have a seat at the table internationally.
Well, I want to go back to Chairman Smith's question about the battery for Dr. Kearns. Can you give us a time frame of when that 5 times more powerful battery? When can we expect this versatile neutron reactor?
Oh, the versatile fast neutron source could be in place pending appropriations in 10 years.
10 years,
Yeah,
okay.
yeah.
When we get a better answer from Dr. Kearns, who said within 5 years.
Yeah, right.
Okay, all right. So
Well, it's nuclear versus battery, sir, so.
So we maybe need to have some bidding going on here. If this legislation is signed into law, what role do you expect INL to play in designing and building this test reactor?
We already have a team formed with actually Argonne and Oak Ridge. My hope is that it would be built at the INL. I've got a place picked out. It's ready to go. But we've got a team formed, so as appropriations comes on, we're ready to run.
Okay, and Dr. Kearns, how about the Argonne National Lab? We seem like we have some collaboration going on here.
Absolutely. And certainly, Chairman Smith paid a very nice tribute, if you will, to Enrico Fermi, really the founding father of Argonne, in his introductory comments. And Argonne's maintained, if you will, a deep expertise in nuclear technology from day one. And we're very actively partnered with Idaho and Oak Ridge, really in terms of development of the new test reactor. We like to think that there's a little bit of argon in every nuclear power plant that's been built, and certainly we continue to really want to participate in a very active way in support the development of the test reactor.
Is it your testimony here today that you'll put pressure on him to get it down to 5 years? Let me ask a question for all in my last minute. Last Congress, the House passed the America Competes Reauthorization Act, which provided national laboratory directors with the flexibility, the ability to authorize cooperative research agreements in priority research valued at up to $1 million. Good thing, bad thing? Dr. Seestrom, I'll go to you.
I think it's a very good thing.
Okay.
These kind of CRADAs advance our interests substantially. I'll just mention one example. Sandia has worked with Goodyear through CRADA mechanism for over 25 years. We brought our advanced modeling and simulation capabilities to their business of designing tires. You might not think that nuclear weapons and tires have a lot in common, but the kind of material interactions that we deal with in both areas are significant.
Okay.
They're able to improve their time to cycle, and we're able to improve the codes that we do for the nuclear weapons.
Perfect. Let me move to Dr. Maxon. Good thing, bad thing?
Definitely a good thing. Well said. I can't add much more. We have plenty of examples, too.
Okay, Dr. Cowell?
Good thing, yes, as well.
Dr. Kearns?
Yes, a very good thing.
Okay, Dr. Peters?
Good thing, and we need more things like it.
Okay, we're working on that. Mr. Chairman, I've got 3 seconds. I yield back to you.
Thank you, Mr. Weber. The gentleman from New York who should have been recognized earlier, Mr. Tonko, is recognized now.
It's all right, Mr. Chair. Thank you, and welcome and thank you to our members of the panel. Our national labs are, I think, a best-kept secret at times and a tremendous empowering resource for this nation. And so, including our national lab at Brookhaven in my home state of New York, you're leading us into the future using fundamental science that will change our understanding of the world around us and our universe. I'd like to continue on along the questioning that Congressmember Bonamici indicated on energy storage. How can energy storage be combined with utility-scale solar and wind farms to help reach our clean energy and environmental goals in the longer term? Dr. Kearns?
Yes, I believe energy storage it would be a great enhancement, if you will, to utility scale solar and wind as well. As you know, those sources tend to be intermittent depending upon the climate and the weather, if you will. And so it's important to have a way to store energy produced in that way so that we can discharge it when needed and really have the additional reserve, if you will. It also provides for a better balance across, if you will, the grid, really allowing electricity to be deployed when and where needed.
Thank you. And Dr. Peters, how could storage better enable a zero-emission hybrid energy system that includes both intermittent renewables and advanced nuclear power sources?
modular nuclear reactors and storage together are probably the way you change the game, in my opinion. The future energy system is probably a lot of renewables and a lot of nuclear, but you have to have storage. But the way that modular reactors work, you can run some modules full out, and others can be modulated to complement the storage. So we're doing a lot of work, actually, INL, along with National Renewable Energy Laboratory in particular, on so-called hybrid energy systems, as you commented on, Congressman. So there's a lot of research going on already, and we're starting to engage industry and both end users, utilities, as well as energy providers to figure that out. But it's a quite exciting area of applied research.
Thank you. And Dr. Maxon, the Office of Science was flat-funded in the budget request, but there were harmful cuts to important research within the Office of Science. The Biological and Environmental Research Program would be cut by 18%. Many would probably not be surprised to learn that BER is the largest sponsor of climate change-related research at DOE, and you talked about that impact on the Earth and environmental systems sciences area. For those in the administration or any that support these sort of cuts, that think climate change is unsettled science, wouldn't it make sense then to further invest in the research to give us a clear answer on the state of our climate?
Well, it's my opinion that understanding where critical elements that drive the Earth's biogeochemical cycles, carbon, phosphorus, nitrogen, sulfur, understanding those things in great detail is really important, not only for climate science, but also for the biological sciences too. So I do see a significant benefit.
Yeah, and I really do believe a lot of our decision-making should be formulated by science and research. Our biological system sciences fared much better in the budget proposal, including increases to genomic science and flat funding for the Joint Genome Institute. What are additional areas of opportunity that we should consider exploring for biological systems sciences?
I think that's a great question. One of the things that I think remains largely untapped is the bringing together of biological sciences and material sciences. I mentioned the Agile Biofoundry that exists to reduce the cost and increase the speed of generating biological products. We don't yet know how to make a lot of things that, for example, don't exist yet. As I mentioned, potentially plastics that have profiles that are improved over others. How about things that don't exist yet? Shatterproof bioglass. Bringing together material science and biological sciences, I think that's a great opportunity.
Wonderful. And in half a minute we have left, what is the status of microbiome research at DOE?
DOE is a leader in microbiome research, along with the USDA, co-chaired the Microbiome Interagency Working Group that put together a strategic plan that I'm hoping will become public someday so we can see what the great opportunities are for the nation's microbiome science.
Wonderful. And thank you again for all the leadership you provide with our labs and for the resource that our labs happens to be. With that, Mr. Chair, I yield back.
Thank the gentleman. Mr. Haltman, you're up next.
Thank you, Chairman. Thank you all so much for being here. I think all my colleagues on this committee and hopefully throughout Congress know my passion for our laboratories and just the incredible work that you all do, and just feel like it is such a vital part of who we are as a nation is our laboratories. And so I just want to congratulate you and thank you and celebrate, but also know that we've got work ahead of us. Specifically for me, having the privilege of representing Fermilab and having Argonne just a few miles outside of my district, I get a chance to go quite often and see the truly groundbreaking work that happens in the breadth of research that is happening just between those two labs, and then you put on top of it all of the other labs. It is wonderful and exciting, but I see unlimited potential if we continue to do the support we need to do and give you all the ability to do the long-term planning and present the visions of what could happen if you have that confidence of knowing that we are supporting you here in Congress. Really, the sky's the limit. So excited about that, and just want to thank you for being here. I had the great opportunity to also visit Sandia last May and Berkeley last September, and each lab was truly uniquely situated and breathtaking. Dr. Peters, since you and I met at Argonne, you've always been an incredibly valuable resource on nuclear security issues, as well as a strong champion for the steps the nation needs to take to realize the next generation of advanced nuclear power. I know Idaho National Lab is proud to have you, but I still kind of like the old name Argonne West. If there's any way you might be able to continue to work on that. One thing, and I'd ask my question for all of you, if you could have maybe a quick thought or statement on this. One thing that I think is important about the work that you're doing is the ability that you have to inspire the next generation of young scientists. Here in the House, we do a congressional app competition, and a few years back, I brought my winner through Argonne's computing facilities to show him what he could accomplish if he continued to learn how to code and improve his STEM skills. Fermi also brings in literally thousands and thousands of students every year for STEM activities, as well as teachers who they train how to make accelerators with high school students throughout the country. I wondered if each of you could talk a little bit about the STEM activities that your lab is involved in, and how much of this is voluntary for staff. At Fermilab, I know we have Science Saturdays, which is basically volunteer-driven. Also, what authority from DOE might make it easier to work with students in classrooms across the country to help to get mentors and experts where they're needed most? Should DOE look at this as workforce development? And maybe we'll just go down the line, start with Dr. Peters, and if you have a thought of what your lab is doing, specifically focused on what we can do to help to increase that.
Yeah, Congressman, great to see you again,
Great
sir.
to see you.
And Argonne's still here.
Good.
But INL is a great place to be.
It is.
We're doing a wide variety of things. Let me take. It is about workforce development. To your final point, we're doing a lot of some direct funding from the government, quite a bit of our own indirect investment going back into it, but also a lot of volunteer. Some examples: we're doing a lot, particularly focused on STEM. No surprise. But trying to bring kids to the lab, much like you see at Fermi and what you see at Argonne, this isn't rocket science, right? You get them in there and get them excited. We're doing a lot of teacher professional development as well, bringing teachers in to show them what we do so that they can get the kids excited. But I love it when the kids actually come to the lab. We're building internship programs, much like I was used to at Argonne, at INL. Just last week, we had My Amazing Future, which is basically Introduce a Girl to Engineering Day, which that's the one that I almost like the most.
Yeah, so
a bunch of 8th grade girls come in and they interact with our scientists. So we're doing a lot. And the state of Idaho, I would also put in a plug for the state of Idaho. The state of Idaho is doing a lot of investment in education, and we're a partner with them on that.
Let me keep going down the line. Thanks, Dr. Peters.
So Sandia has a modest number of outreach activities. One I'll mention is at our Advanced Materials Laboratory, which is joint with the University of New Mexico, where we bring in a set of elementary school students to see the cool things you can do with materials. Mostly we're funding that out of indirect and volunteer labor. We're keen on internship. As I travel around Sandia and see the young engineers and scientists, many of them came to Sandia because they were interns, and we are not so well known as Fermilab and Argonne, and so getting these young people in the door, and I'll call it the last thing, is we recently established as a new management team, the Jill Ruby Scholarship to honor our previous laboratory director, Jill Ruby, as the first woman director of a national security lab, and we're about to announce our first 2 winners of that prize to bring 2 outstanding young women scientists into the lab.
Great idea. My time's expired. If the chairman would give me leeway just to quickly, the other 3, if you could just mention a thing or two. Thank you.
Yes, thank you. The Joint Bioenergy Institute, which you visited last
great.
fall,
That's awesome.
has a program focused on high school students that are underrepresented minorities who then go through a summer internship and research opportunity that has, over the last 10 years, generated over a 95% college acceptance rate on those students.
Fantastic. Dr. Cow.
So for SLAC, we try to leverage the funding from the department. Recently, we actually working with Moorfund Foundation to encourage girls in middle and high school to come to the laboratory, because I think we need to do more to build a pipeline for more diversified workforce for us.
I agree. Thanks. Dr. Kearns.
Yes, Argonne has a very active educational program, a great outreach program. One thing that's coming up that I'll mention is activities supported by the Department of Energy's Office of Electricity called the Cyber Defense Competition.
Great.
We actually bring students into the laboratory We set up a green team, red team, and a yellow team, basically, including representatives from industry, and of course, it's a bit of a hackathon, if you will, and the students compete against each other, various schools. We've got 210 students participating this year. Pacific Northwest National Laboratory and Oak Ridge National Laboratory have also joined the activity, and so we're pretty excited about that. It happens here, April 2nd at Argonne. So if you're in the neighborhood, please.
I'll do my best. That sounds great. Thanks, Chairman. Thank you all so much, and yield back.
The gentleman yields back. We will yield to Mr. Foster of Illinois if he brought a pie for Pie Day.
What? Yeah, well, it is it's in the back room there, but if the staff will bring out the remaining crumbs, if they haven't already pounced on it.
The gentleman's recognized.
I want to wish everyone a happy Pi Day. It's a day where we celebrate the rational arts of logic, science, mathematics, with an irrational number. It's a number whose digits continue as long and as randomly as, I don't know, politicians' tweets, perhaps. But I want to thank you all for coming here.
The gentleman's time has expired.
I sometimes introduce myself as representing 100% of the strategic reserve of physicists in the U.S. Congress. I also represent the 11th District of Illinois, which includes Argonne National Lab, and before coming to Congress, I worked at Fermilab for 23 years. And so I have a special interest among the just incredible scientific facilities that you operate in Argonne's facilities, including the Advanced Photon Source. On a recent tour of the national labs with Secretary Perry, where we visited both Fermilab and Argonne, and I spent the day with him, I was really impressed by his enthusiasm for the crucial science and the research conducted at the labs. You live in a situation where you have political oversight at the very top levels. In previous administrations, we saw a very strong scientific component at the top levels of the administration. That doesn't seem to be as present in the current administration. And when we've had, the political level of appointees and below, before this committee, they have acknowledged that and said how much they depend on the scientific expertise at the labs. And so your role there is more crucial than ever. And I want to thank you for toughing it out. And we're doing our best to protect you from the proposed budget cuts that would make your life miserable if they came through. Among other things, they would halt the Argonne's Advanced Photon Source upgrade, which would allow Argonne to rejoin Dr. Cowell's lab at the very forefront of leading light sources in the world and the incredible things that you can do with them. I have actually one specific question on energy storage, where I'm working now on a bipartisan bill with Representative Knight, talking about trying to set up demonstration programs for grid-scale energy storage. And when you set up a program with specific goals, it's important you set the goals right. I think it's one of the most destructive things we can do is to ask a group of talented technical people to do something that they know is impossible. An example of that would, say, be going to Mars on a flat budget, which is something we routinely ask NASA to do. So there's three specific goals that we're thinking of right now. First, to have an installed energy capital cost of $100 per watt, and a minimum of one charge and discharge cycle every day. It's a grid scale thing, and a lifetime of 5,000 cycles of discharge and charge at full output. And you can respond either now or for the record. And whether those are sufficiently challenging to get the next generation of people interested in it, and sufficiently achievable that you're not just asking people to go to Mars on a flat budget. And so I'd be interested if you have any immediate reactions to those, if they're in the ballpark. Because there is a bipartisan interest in, including by our committee chair, in making the transition to an energy economy that doesn't dump large amounts of carbon dioxide into the atmosphere, and energy storage is crucial there. Yeah,
let me respond by initially, and then also promise some follow-up in terms of a more formal submission. But those look like they're in the ballpark to me. They look like they're aggressive enough and yet realistic enough in terms of where we're at today and where we'd like to drive. I guess the one question I might have in terms of follow-up is the time frame as to when you would like to achieve these goals. Any established?
Well, these would be actually choosing and starting the projects 3 to 5 years from now.
3 to 5 years, okay. So maybe let me get back to the lab and ask a few folks that have greater knowledge than I do on this subject to make sure that we're responding appropriately. But I'd say they're in the ballpark.
Yeah, thank you. Any other reactions to that?
We'll take it offline and bring you back an answer.
Yeah, but I concur. They sound properly aggressive, but I think we need to take it for the record, so.
Yeah, it's tough. You can't, President Kennedy said we're going to the moon within a decade because there were detailed parameters for a mission to the moon that could be achieved with known technology at the time.
Right.
And so it's a very different thing. It doesn't mean it's easy, doesn't mean it's certain, but it's important that we set those right. And, I really want to take advantage of that bipartisan enthusiasm for transitioning to a low-carbon economy. And I am now 0 on my clock. So thank you. Yield back.
Okay, the gentleman yields back. Thank you. Dr. Babin, you're recognized.
Yes, sir. Thank you, Mr. Chairman. I want to thank all of you witnesses for being here today. Very interesting, very valuable information. Dr. Kearns, I have a couple of questions for you, if you don't mind. At Argonne, a team of researchers discovered a way to attach oil-attracting molecules to polyurethane foam, that the same foam commonly used in furniture and insulation, by priming it with a metal oxide glue. The new and reusable material, called the oleo sponge, can absorb oil from an entire water column, not just up at the surface. The sponges will be used to clean up oil spills as well as diesel and oil buildup in ports and harbors. And what collaborative efforts led to this technological breakthrough? And what about the research environment at Argonne that developed this technology? And what steps will be taken by Argonne to transfer this technology to the fossil fuel industry? And I will repeat that if you answer the first one and then don't remember what the second one was.
Thank you. Thank you.
Okay.
Yes, the oleo sponge is a very exciting development. It's really, Genesis, if you will, was really funded through the Laboratory Directors Research and Development Program, the LDRD program mentioned earlier by Dr. Seestrom, as really essential, if you will, to really allow the laboratories to really develop new thoughts and pursue new ideas. And so its initial funding was provided through that vehicle. It also built upon some capabilities that the Office of Science, the Basic Energy Sciences Program, funded through the Center for Nanoscale Materials, really. And it's a cross-collaboration between two different divisions at the laboratory, one very basic in terms of its approach at the Center for Nanoscale Materials, but one more applied in terms of the Energy Systems Division at the Argonne. So great story in terms of where it began, really building off that initial investment by the Office of Science and further developed with LDRD funding, and then really a cross-laboratory collaboration. In terms of what's occurring as we work to commercialize that technology, an opportunity announcement was made, I'd say 8-10 months ago. Response has been tremendous. We have over 140 companies that have reached out and expressed an interest in the technology, and we've been in serious conversation with several since that time. We're down to a handful of folks that we're talking to currently that might take an interest, if you will, in terms of application of this particular technology. And develop it for commercial products.
Great, that's excellent. And Dr. Seestrom, did you have anything you wanted to add to that since you were involved in it? Okay, all right, thank you. And also, Dr. Kearns, the Technology Commercialization Fund allocates 0.9% of the funding from the Applied Energy Offices to invest in commercialization of energy technology. When I look at this program and the decision under the Obama administration to establish the Office of Technology Transitions, I'm concerned that we're consolidating funding decisions in Washington instead of giving more flexibility to our national labs, which tend to have direct relationships with industry and better understand the technology needs. How can Congress work with you to ensure that we don't centralize our technology transfer programs in Washington, which we're trying to not do?
Good question. I think there are a number of things that could be done. One is the labs do, as you suggest, work directly with industry. A good example of an outreach activity at the Argonne National Laboratory is really we held an industry day focused on energy storage, and we had over 100 companies come to the lab really to learn about our capabilities and express interest, if you will, in terms of their needs, their desires for further development of their ideas. And as a result of that, a handful of opportunities to develop into CRADIS, cooperative research and development agreements, and other examples of the laboratory working side by side with industry in that way. So that's one great example, I think, of how to work with industry. What you might do is really encourage, as was discussed earlier, encourage more vehicles like the Cooperative Research and Development Agreement and the Strategic Partnership Project efforts the Department of Energy has underway. I'd also say the Technology Commercialization Fund you mentioned has been very active. Argonne's been very active, and it's been a very attractive program for our industrial partners in that way as well. So good history, good record there in terms of accomplishments.
Okay, that's great. Well, Mr. Chairman, I'll yield back 8 seconds. Thank you.
The gentleman yields back. Thank you. And Mr. Dunn, you're recognized for 5 minutes and 8 seconds.
Thank you very much, Mr. Chairman. Thank the panelists for coming here today to inform us about your labs. I look forward to coming to visit you at the labs, and probably a lot more informative visit when you can actually teach me into place. I'm a physician. I'll tend to focus on healthcare in my questions. And if I could start with Dr. Kearns. Millions of people around the world have been helped with medical isotopes in the use of diagnosis, treatment, imaging, and other diseases, cancer and whatnot. We lack the capacity in the United States to produce all the needed isotopes, and some of our isotopes are in fact produced in highly enriched uranium reactors, which carries proliferation risks. Your lab is helping 2 companies develop new methods to make these isotopes in accelerators rather than reactors. I'd ask you to explain why it's important to the medical community to have these isotopes and to the patients to have these isotopes, but also why avoid the highly enriched uranium reactors.
Yeah, the last question first, fairly simple to understand. With the use of highly enriched uranium, the concern is one of proliferation and really safeguarding, if you will, the materials in a way that doesn't allow them to end up in the hands of those who might wish ill on individuals or nations, and so that's really the key component there. Certainly, one of the primary examples, and the other laboratories involved should, I think, in the isotope program should also comment, but the one program that's been active at Argonne has been the Moly-99 program, which is funded by the NNSA, working with a couple of industrial companies, if you will, to commercialize that technology. It's a great example, really, again, of industry laboratory partnerships and really driving towards a well-defined outcome, if you will. I think the why do that Moly-99 is pretty essential, really, in terms of how we conduct medicine today. It's critical for the United States because we don't have any domestic production of Moly-99 currently. We're really dependent upon foreign sources, and of course the reliability of those sources is from time to time of concern. And so
it's actually interrupted my practice on occasion.
Oh, has it?
And I'm sure I'm not the only one.
Yes.
So it's important for us to be able to get to those. Now, some of the isotopes simply cannot be produced in a reactor, in a accelerator. They need a reactor, and I know in recent years we've pushed to move from HEUs to low-enriched uranium reactors, and I understand that. I'm on board, but the low-enriched uranium reactors generate roughly 10 times the radioactive waste as the HEU reactors, and the United States has zero capacity to reprocess radioactive waste at this time. I believe I'm right on that. There's no MOX plants in the U.S. Dr. Peters?
There's not the capability to reprocess currently in the United States.
And the MOX plant that's been under construction in South Carolina is slow or off track?
It's behind schedule, over budget, and it's dedicated to reprocessing of the 34 metric tons of surplus plutonium.
Okay, so that's
it's not going to reprocess HEU.
Okay, well, that's worth knowing. Thank you. So I invite all of the panelists to bend your considerable talents and resources to solving the problem of reprocessing our domestic radioactive waste, which should not be treated as waste in the first place, but as a valuable precursor commodity. And I think we all know that the second generation radioactive waste that comes out of these reprocessed and reused, that you've changed the half-life of those that radioactive waste on the far end of the cycle. to something that's logarithmically less, right? I mean, we move from hundreds of thousand years, millions of years half-life to hundreds of years half-life. So I would encourage everybody to solve those problems. I know you can do it. I have faith in you. I'm going to sneak in on another question, if I can, on the ultra-fast, this is to Dr. Cow, the ultra-fast frame rate x-rays you use to capture molecular movies. Fascinating stuff. I've seen some of the work that's available. Can you explain how we use that information on a molecular level and how it might pertain to healthcare?
Okay, so what the ultra-fast X-ray does is you can take snapshot of a protein that typically these are targets for drug development, and in particular those on the surface of a membrane protein. They are very difficult to crystallize into crystals, so they tend to be very small. And so with this ultra-fast X-ray, you can take snapshot of these, and you drop them down into the X-ray beam. You hit it, it disappears, but you capture the image. You do 1 million shots of these. You then reconstruct the three-dimensional atomic structure of that. And then you can use that to guide you to develop drugs.
Thank you very much, Mr. Chairman. I yield back.
Gentleman yields back. The gentleman from Louisiana is recognized for 5 minutes.
Thank you, Mr. Chairman, and I thank this brilliant assemblage of scientists before us. Your testimony has been personally inspiring to me. Historically, DOE's research programs have had the greatest impact when resources are focused on completion of certain goals or missions. Our national debt certainly leads us to righteous funding restrictions at the federal level, and that should lead us to a focus on result and mission-oriented research. In my opinion, this is particularly true for advanced nuclear power. New modular technologies hold great promise and should be a priority for the department. I believe we should establish a clear set of goals for completing a program leading to the demonstration of new nuclear technologies, real technologies, achievable technologies, technologies that can be deployed. Earlier this week, I introduced legislation H.R. 5260, the Advanced Nuclear Energy Technologies Act, which would set a goal of demonstrating 4 commercially competitive advanced reactor designs over the next decade. Setting mission-driven goals at DOE will help the U.S. regain its global leadership in nuclear energy security, open new markets for domestic power generation, retake a key strategic advantage from China and Russia, and put thousands of American engineers, manufacturers, and tradesmen to work. Further, a robust American nuclear energy sector is essential to President Trump's vision of American energy dominance. Dr. Peters, how can we better utilize DOE's nuclear programs to expedite the demonstration and ultimate commercialization of small modular reactors?
Thank you, Congressman. First and foremost, let me say that I support what you're trying to do with your legislation. As you know, there's similar legislation coming out of the Senate to look at 4 demos roughly 10 years from now. But I'm a big supporter of trying to start to drive the R&D program to cost targets to try to drive down the economics of nuclear systems. I think that's important. So the R&D needs to be done now to help get us to that aggressive demonstration goal that you articulated. I would also want to say that in addition to the versatile fast neutron source, which this committee is already fully supportive of, being able to go actually build these prototype demonstration units would be really, really important for putting us back in leadership position, because other countries are doing this. China's building these, prototyping all of these advanced concepts, so it's very important. The other part of this is that where would you put the demos? A place like INL would be a place you could build these demonstrations. Be happy to do that.
Thank you for your answer. Do you concur that a demonstration of a working prototype is certainly the link to a public-private partnership?
It is, because I mentioned earlier about the private sector needing capital, but it's going to have to be a partnership with the government. But I do believe if we get those out to first-of-a-kind demonstration for some of these advanced concepts, that will then enable them to get into the market and move very quickly and penetrate the market.
Thank you, Doctor. Dr. Kearns, you have anything to add?
No, I think I fully support what Mark has responded with. I think we're good.
Well, I have an additional question a bit that hasn't been really touched on here today. Please respond as you see fit. What steps do your labs take to protect the classified, intellectual, and proprietary information and property from access, copying, and theft by foreign nationals? Any member?
So, of course, at Sandia, as a national security lab, we place the highest priority on protecting our classified. We have very few foreign nationals, mainly accessing only external areas of the lab.
You feel comfortable that your lab is sufficiently protected?
I do. I would say I am as worried about insider threat as I am about foreign nationals.
As we should be. Does anyone else have something to add there?
Well,
We're very concerned about intellectual property theft.
Yeah, maybe a little bit on the industry engagement, perhaps. I mean, all of us, I'm sure, we have extensive controls in place, non-disclosure agreements and whatnot, so that when we engage industry, we protect that information. And as you heard here, all of us are looking to increase our industry engagement, so that's very, very important. But we all have the ability to control the culture of the labs because we're dealing with classified material throughout our history. I think the industry engagement really is treated in a very similar way. We have to protect this information very, very carefully.
I thank you all for your answers. My time has expired, Mr. Chairman.
I thank the gentleman. Mr. Biggs, you are up next.
Thanks, Mr. Chairman. And I, too, thank Chairman Smith for inviting you. And this is an august panel, and it's been very informative, very, very interesting. And I've learned a lot. And I just am very impressed at what we've talked about today. And thank you for being here. Dr. Seestrom, after a tsunami damaged the Fukushima Daiichi nuclear power plant in 2011, massive amounts of seawater cooled the reactor. During cleanup activities, a molecular sieve created by Sandia National Lab scientists was used to extract radioactive cesium from tens of millions of gallons of seawater on the reactor site. It's my understanding that this technology was developed using laboratory-directed research and development, LDRD, funding at Sandia. Can you tell us a little more about how the technology was developed and how it made its way to Japan to play such an important role in the cleanup?
So thank you very much for that question, Congressman. This is actually quite an informative story. So as you probably know, molecular sieves are crystalline substances, and the size of the pores limit the size of molecules that can go through. So the particular technology that was developed at Sandia, in one of our earliest CRADA work with industry, crystalline silicotitanate had specific strength for removing cesium. We had a partnership with a company called UOP, actually based, I think, in Des Plaines, Illinois. We licensed it to them. This was back in the 90s. Won an R&D 100 award based on that. When Fukushima came along, one of our eminent senior scientists, the chemist Tina Nenoff, who had worked on disposal of wastes and cleaning of products at Hanford for a long time, was able to quickly test the CST for its applicability to putting the seawater through it, found that it would work just fine, and UOP managed to work with TEPCO in Japan to put that on the ground there.
It's fascinating. That's a great story. So you've talked about LDRD funding being a key part of how the labs pursue new research opportunities. What steps can Congress take to facilitate more of this flexible but mission-focused research?
We'll continue the good work that Congress has done in setting both an upper threshold and a lower threshold for LDRD. We value every penny of that research. I could, if we had time, give you a list of 5 different inventions that came out of our LDRD program that transformed our missions, including our work in rad-hard micro semiconductors. So just keep the limits there for us.
And so I want to talk about the budgeting because people talked about the CRs and its detrimental impact on all of you. But I'm new to Congress, and we're going to vote on our 7th CR in 6 months, and I'm kind of embarrassed by that. I hope there's not enough people in here to join me in my embarrassment. But over the last 20 years, we've done more than 100 CRs, an average of 5, in excess of 5, almost 6 CRs per year. And I realize that it's detrimental, but Is it baked in at all in your budgeting as you you know, the fact that it looks to me like budgeting in some ways is actually reasonably stable, but with this kind of crazy blip every 2 or 3 months where we say, well, we're going to shut down government for a weekend or whatever it may be. Is it baked in at all, or can you elaborate on that? I guess what I'm trying to say.
Well, given that it's as you note, an annual occurrence, we understand how to manage through it, but I would never say that it's a good thing, because it's the constant challenge to keep the staff excited and motivated when you're going through this. Particularly, I'll also particularly note the early career staff. Who, some of us, we've been through this for a long time, but the early career staff watch this and they say, why am I at a lab? Why don't I go work somewhere else? So it's a challenge. So the more we get to regular order and stable research funding, the better we can innovate.
Well, don't get me wrong. I'm not saying that that's the way to do it. I'm all with you on a.
Yeah, I understand, but it does. But I'm just reacting to it's baked in the sense that from the management perspective, we know how to manage it. But that doesn't mean that the staff don't get put through a lot of churn.
Yeah.
But I would say we're all used to, after 30 years, seeing continuing resolutions for a month or two. But the length that we're going now is really hard to deal with, and programs begin to lose funding, and it's particularly hard on new starting projects, which can't get going in a CR.
We did one from December 8th to December 22nd this year. How idiotic. I mean, last year. Anyway, sorry, Dr.
Yeah, I was going to comment as well. I think a couple of things. And one is it is particularly difficult for early career scientists because it creates uncertainty. And, of course, they have lots of opportunities to go other places, as has already been mentioned by the panel. I think it's critical that during this time of uncertainty, the laboratory directors need to show some leadership and really step out front and talk about it being a process, and also share our experience in terms of positive outcomes. I would also say, though, it really is, has just been commented by Susan, in terms of impact on new starts or construction activities, or perhaps not a new start, but where a ramp up in funding is really planned for an ongoing project is particularly critical. You know, certainly the advanced photon source at Argonne has suffered this time and time again, and so we're really pleased with the indications of the FY18 budget, and hopefully the FY19 budget will show a different story, but really it creates a lag, takes away a sense of urgency. It really kind of challenges us to really stay at the edge in terms of our thinking, so it's important that we're able to move forward.
Yes, and I will just tell you that I'll keep pushing for us to do an annual budget so everybody can be more stable and more predictable. So, again, thank you for being here. Thank you, Mr. Chairman.
Mr. Norman, you are up.
Just echo what Congressman Biggs says about the CRs. You can't run your business on a month-to-month basis, nor should we expect you. Thank each of you for your testimony. Dr. Peters, in your prepared testimony, you talk about the work that the Idaho National Lab is doing to support the existing light water reactor fleet, like developing the new accident-resistant fuels or working with utilities to modernize nuclear power plant control rooms. What other research is the lab undertaking to help nuclear energy technology remain competitive?
In the light water reactor area, we're also working on materials. So, because when a utility wants to take a reactor from 20 to 40 to 60 or even 80 years of operation, we need to ensure that the materials will survive that long. We see no showstoppers there, so all indications are they'll be fine. In the advanced reactor area, where we're working with a lot of companies in partnership to help them mature their designs, make them more cost competitive. Everything from the reactor core itself to the fuel. We do extensive work on fuel development. So you mentioned accident-tolerant fuels that would go into the light water reactors, but also developing advanced fuels for advanced reactors. We're working a lot. We haven't talked a lot about it today, a lot on the nuclear fuel cycle. So as you know, we're pursuing going to a repository now, but could there be options for reprocessing in the future? We're doing a lot of research in that area as well. But I want to stress, we're an applied laboratory, so we work very closely with industry across the whole gambit, and that's an important part of our focus.
Related to that, Dr. Peters, is there a direct benefit to the DOE, Department of Energy, to have the labs perform multidisciplinary science research for different programs across the department? As an example, how does it benefit the Office of Science or NNSA to have the respective labs engage in diverse research for other DOE programs or federal agencies?
We all have unique capabilities. So I very much think that, for example, Sandia or Argonne is two good examples, have capabilities that they've built in either the security or the basic science area that are very applicable to the applied programs. We partner very, very effectively. If you look at the capabilities of the 17 labs, some would argue you see duplication. I actually see a lot of complementarity. So there's tremendous opportunity. And we're an applied nuclear lab, but we do a lot of work in the national security space and cybersecurity and whatnot, because we have capability that can solve national problems. So collaboration's really important across the system, and I think it's quite effective, actually.
Makes sense. Dr. Seestrom, as a nuclear weapons lab, Sandia has a specific mission to accomplish for DOE. But from your testimony, it sounds like the impact of Sandia's research has been much more broad. Can you provide some examples of areas of research that Sandia conducts for its nuclear weapons mission, but that has also led to benefits in the civilian economy?
So, Sandia has expertise in hydrogen materials coming from our mission in NNSA for gas bottles. That leads us to certain expertise in chemical processes. In our combustion research facility, we do research with each of the major U.S. car companies, looking at improving fuel efficiency for light-duty and heavy-duty trucks, as an example. We have thousands of Kratos there. Our work for NNSA, where we're responsible for radars, have led to other national security work, where for the DoD, we've developed a next generation of synthetic aperture radar, which lets us save our troops on the battleground with much better visibility through clouds. That comes back to impact our core national security mission.
What about manufacturing?
I don't think I can answer on manufacturing, but I'll take that for the record.
Okay, thank you. I yield back.
I thank the witnesses for their testimony and the members for their questions. The record will remain open for 2 weeks for additional written comments and written questions from members. This hearing is adjourned.